Hello everyone, and welcome to this video on logic gates and circuits. In this video we will be covering the following. What are logic gates? The 7 types of logic gates. The equivalency relationship with the AND or NAND and NOR gates. Using combinational logic to create gates from other gates. What are the universal logic gates? Emulating gates with the universal gates. And what is logic and scaling of logic circuits? Logic gates are the lowest level of abstraction in computer design. Anything lower than that, and are getting to the physical implementation of that logic. Logic gates can be implemented to a variety of different mechanisms: pneumatic circuits, electromechanical relays, transistors, and redstone from Minecraft. Logic gates process binary data. Each logic gate is a function which takes in one or more binary inputs and returns a singular binary output. These binary values can be expressed in many ways. For example, ones and zeros, true and false, on and off. Each logic gate can be described by a truth table. Truth table showing the various input states and the corresponding outputs. There are 7 basic logic gates, 3 of which are considered to be primitive logic gates. They are AND, OR, and NOT. They can be used to make the combinational logic gates, which are referred to as NOT AND or NAND, NOT OR, NOR, exclusive OR or XOR, or exclusive NOT OR, XNOR. The AND gate returns true when A and B are both true. OR returns true when either A or B are true, and NOT returns true when input is false. The NOT AND gate has opposite outputs for the same inputs as the AND. The NOR gate has the opposite outputs for the same inputs as the OR gate. The NAND gate is false only on one condition: when A and B are both true, and the NOR gate is only true when A and B are both false. The exclusive NOR gate is similar to OR as well, except it excludes A and B as a true condition. It returns false under those inputs. It is also often referred to as the difference logic gate because it returns true when A does not equal B. Exclusive NOR has the inverted output of XOR, and it is often referred to as the equals operator because it returns true when A equals B. The NAND gate and the NOR gate are also classified as universal logic gates, and we get to why that is later in this video. The 4 logic gates, AND, NAND, OR, and NOR, have a special relationship with each other. With only one of them, plus NOT gates, you can convert a starting gate into the 3 other logic gates. This can be done by either passing the inputs, outputs, or both through a NOT gate on entering or leaving that gate. Sending an input or output through a NOT gate is often referred to as negating that input or output. Looking at the diagram to the left, we can see how one gate can be made to function like another. Negate the output of any gate, and it will become equivalent to the gate horizontal to it in this diagram. Negate its input. It will become equivalent to the one diagonal to it in this diagram. Negate both input and output. It will become equivalent to the one vertical to it in this diagram. So how does this work? Well, if you have an AND gate and you negate its output, it's obvious it will become an AND. And if you negate a NOR, it will become a NOR. And if 2 NOTs in a row cancel out, then NAND, NOT in NAND will turn it back to an AND. If you negate the inputs of an AND, well, AND is true when both inputs are true. If the inputs are negated, it will become true only when both inputs are false, which is equivalent to what? A NOR gate. If you negate the inputs of the OR gate, it'll go from, if either input is true, to either input is false, and therefore it will return false only under the condition of both being true, aka a NAND gate. To get back to how we can create logic gates using a combination of the three primitives, here is an XOR gate circuit. We start with the OR gate, which for the most part is what we want. However, we add AND gates to its inputs. And by doing so, we make it so each AND is either A, not B, or B, not A. By doing this, if A and B are both true, the ANDs will return both false, and the OR gate will return false. However, under A or B being true, one of the ANDs will return true, and the OR will return true as well. The logical expression for this can be referred to as A and not B, or not A and B. Essentially, one input is nullifying the other. As I mentioned earlier, the NAND and NOR gates are universal logic gates. So what does that mean? Well, using logic circuits containing only NAND or only NOR gates, one can emulate all other logic gates. So how does one emulate a NOT gate with the universal gates? Well, one can emulate a NOT gate with a NAND or NOR gate by splitting the IN input into both the A and the B inputs of either the NAND or the NOR gate. The resulting gate will function like a NOT gate. So now one has an emulated NOT gate and either a NAND or a NOR starting gate. Now, remember the equivalence relationship diagram shown earlier that says we have a NOT gate and one of those four basic gates, we can make all the other gates? Well, look who's present. The NAND gate and the NOR gate, and both of which can emulate NOT gates. So we can make all four of these gates. These diagrams depict circuits in which AND, NOT, OR, and NOR are being emulated with only NAND gates as their components. And here are logic circuits emulating the OR, NOT, and NAND logic gates using only NOR gates. And on to our last topic, scaling logic circuits. Some logic circuits can scale the number of channels, bit width / bus size, or both. A regular AND gate has only two input channels, A and B. Each input channel and the output has a bit width of 1 bit. Now what if one wants to test if all four inputs are true? Four-way AND. Now what if one wants to do a bitwise logical operation, like 3-bit AND, as shown there? How would you do it? The following are examples of applying scaling to an AND logic gate. In the first column, you'll see two examples of a four-way AND, which takes in four inputs, A, B, C, and D, and returns true if all four are true. In the middle column, you see a 3-bit AND. It takes two 3-bit inputs, A and B, and does a bitwise AND. As such, out 0 equals A0 and B0. Out 1 is A1 and B1. Out 2 is A2 and B2. So it returns a single 3-bit output. In the last column, you see an example of a 3-bit 3-way AND, which takes three 3-bit inputs, does a 3-way bitwise AND, and returns a 3-bit output.